Okay, we're back to dynamic games. And games, it's like you can describe them in a tree form. So in the previous chapters, we analyzed mostly simultaneous strategic interactions where players choose their action simultaneously. Like Prisoner's Dilemma games or any games in a table. Typically, all of them are, the assumption is that the game is played simultaneously. We had two exceptions. One of them was that we analyzed, in the case of choosing a strategy to a firm with 3 board members, 3 strategies, that we distinguish if the selection is done simultaneously by voting or by voting in a sequence. Okay? The sequential, when we analyze the sequential process, then we really used the backward induction way of thinking. There was another example where IBM versus JBM, and that was to analyze. IBM decides about some software to develop. JBM sees what IBM does, and so this is also was an example that goes by sequence. First IBM as a leader, then JBM as a follower. But let's talk about general games that are played sequentially. So let's start with a very simple example. A brand company B controls the market for air conditioning units. Okay? A new company E for entrant is about to enter this market. If E enters, B has 2 choices. To accommodate E, okay, let's compete with the entrant. By accepting a lower market share, if I have to compete, I have to maybe reduce the price. I'm also getting smaller market share. Or I can fight a price war so that the entrant will leave, or by convincing the entrant that that's what I'm going to do, that entrant may not come in. So let's describe it in more details. If B accommodates the entry, not fighting, E will make a profit, the entrant will make a profit of 100,000. But if B starts a price war, it will cause E to lose 200,000. If E stays out, its profit is 0. The outcome for E is described by the following tree. Okay, so let's look what can happen. So E start by saying maybe I should enter or stay out. If I stay out, nothing, 0. If I enter and he's not going to fight with me, the brand, the incumbent firm, B is the incumbent firm brand, then I'm going to make meaning E is going to make 100,000. If he fights me, then E is going to make negative 200. If she stays out, 0. But what is missing is what happens to B. Suppose next that B as a monopolist is able to make a profit of $300,000 as long as E is out. Sharing the market with E reduces its profit to $100,000. First, they have to reduce price because so the total income is going to be down. Fighting a price war will leave B with a very small, relatively small profit of $50,000. So now let's see the entire game. So E can enter or stay out. If he stays out, he gets 0. And actually, the brand, the incumbent, gets a monopoly profit of 300,000. If E decides to enter, then B should decide whether to fight or to accommodate. If he fights, the entrant loses 200,000. Why? Because to enter it's costly, and if she enters for nothing, she's going to lose her investment, $200,000. While the fight will reduce the profit of B from $300,000 to $50,000. If they don't fight, and they compete with each other, then each gets 100,000, total 200,000, obviously below the monopoly profit, which is the highest possible. So this is the game, and we have to analyze it. So we start from the last point. Okay, let's talk about B here. I'm not sure that maybe E will stay out, but what happens if E enters and B has to make a decision? So she says the following: if I fight, I'm getting 50,000. If I accommodate, I'm getting 100,000. So if I have to make a decision to go for 100 or to go to 50, clearly I'm going here. E knows it. He knows that if he is going to enter, then B is going to accommodate, and therefore he will make 100,000. Okay, and if he stays out, he gets 0. So he has to compare the 100 with the 0, and since 100 is more than 0, he goes here. The only outcome is they share the market 100-100. You see, E will decide to enter, knowing that B decides to accommodate. So let me now erase this to allow a better... Okay, so B makes the first decision, and she wants to accommodate because she compares 100,000 to 50,000. E then has to make a decision to enter and to get 100,000 or to stay out and to get 0. So he enters. Looking ahead and reasoning back, we can see that if E enters, then the best reply strategy of B is to accommodate E, since 100 is more than 50. E takes this into account and chooses to enter to obtain 100,000. Okay, so this is the result. This is the outcome. Suppose next that there is uncertainty about the profit of B if he enters. Suppose that he believes that in case B fights, B will obtain either $50,000 or $200,000, okay, or $60,000, each with probability 1/3. So either 50,000, 200, or 60, each with probability 1/3. If B accommodates E and doesn't fight, then it will obtain, okay, 100,000 with certainty. The uncertainty is what happens to B if she fights. If she doesn't fight, they together, stay, they will split the market, which will reduce from 300,000 to 200,000 total, and they will split it equally because they are not anymore monopoly, and therefore the total profit goes down. So here is the situation. So he knows, let's start. If he enters, what happens? B has to make a decision. Accommodate, and in which case she's going to get 100, or to fight. If it fights, N is for nature. Sometimes it's called chance move, and think of it as God decide what will happen. Is with probability 1/3, B will make 50,000. With probability 1/3, B is going to make 200,000. With probability 1/3, B is going to get 60,000. In all cases, since N is going to fight, E is going to lose $200,000. As before, if E stays out, 0 for E and 300 for B. So this is the new game. Okay? So let me try to analyze now this game. And again, by what we call backward induction. So first of all, I want to find out what is all this animal. So with probability 1/3, as for E, he gets negative 200 no matter what. So he's guaranteed to get negative 200. What is the expected profit for B? It's an average. It's a 1/3 times 50,000, 1/3 times 200,000, 1/3 times 60,000. So this is a regular average. So what is it? 50 plus 200, 250 plus 60, 310. 310 divided by 1/3, this is the average. So now, in this case, if E enters, B knows that if she fights, she gets on average this much. If she doesn't accommodate, she gets this much. If she's just looking to maximize her expected profit, she is going to go to fight. Gives her more. E knows it. He knows that if he enters, B is going to fight, and therefore he's going to end up with negative 200. If he stays out, he gets 0. So what will happen? Obviously, he, in this case, will stay out. Let's see. So this is, by the way, so I'm going to replace all this animal by this amount. Because I know what happens if I go to fight. Then E gets negative 200,000 and B is going to get an expectation that much. So I replace a new game which is equivalent. Enter or accommodate 100 and 100. Fight is this. And stay out is this. So if B fights, it will obtain an expected payoff of all this, which is 103,333 and 1/3. If B accommodates, it obtains only $100,000. The resulting tree is this. And now let's see the decisions. So B here compares 103,333 with 100, and she is going to fight this time. E understands it, and if she stays out, she gets 0. Otherwise, she's going to lose 200,000. So E here will stay out. And what is the outcome now? A different outcome. It's this one. Hence, B will fight, and E stays out. Solving dynamic games in a tree form, where you can describe it by a tree. I can go here or here, you can go here, here or here, etc., etc. By backward manner always yield a Nash equilibrium. This claim needed to be proven, but take it for granted. Let's say, even if you want to see this, let's say just as an example I can show you, but I have to say that the way the Nash equilibrium, which is obtained by backward induction, is always better, because the other equilibrium will be such that one of the players must play weakly dominated strategies, and therefore it's not going to be sensible. Only the one that will be obtained by solving the game backwardly is going to be the sensible one. That is the reason we called such an equilibrium perfect equilibrium. Perfect applied only to games, dynamic games in a tree form. Okay? If I'm playing simultaneous game, there is no meaning here for perfect equilibrium. Actually, there is another definition for perfect equilibrium that applies for any game, but the backward induction can apply only to dynamic games. So look on this. To see this, let us examine the game in figure 2. In order to find all the Nash equilibrium of this game, the idea is, if you want to find the equilibrium, transform the game into a game in strategic form as if they two play simultaneously. E decides whether to enter or stay out. At the same time, B decides to accommodate or to fight in case E enters. So the strategic form of this game, now I put everything in thousands of dollars. I'm talking about the original one. The first one with full certainty. Look, let's see. E can either enter or can stay out. Enter or stay out. Okay, if E stays out, doesn't matter if B accommodates or fight, that is the outcome. 0 is 300, 0 is 300. Why? Because E stays out. So even if B decided to accommodate E or to fight E, if E doesn't enter, then she doesn't implement her strategy, and therefore E gets 0, is out, and B gets 300,000. However, if E enters and B accommodates 100 and 100, and if she fights, then negative 250. Remember, in this case, the equilibrium was, the equilibrium, let me take it out, let's remind you, backward induction here, I compare 100,000 to, who makes a decision here? B. What's the payoff of B? 100,000 and 50,000. If B accommodates, she gets 100,000. If B fights, she gets 50,000. Since 100,000 is more than 50,000, then clearly she must fight. She must accommodate to get 100 and not 50. He knows it, and he says, if I enter, I'm going to get 100. If I stay out, 0. So the only perfect, what we call perfect equilibrium, or sensible one, is that E enters and B accommodates. So this is the only equilibrium, sensible equilibrium. Also, first of all, let's check that it's an equilibrium, clearly. 100 and 100 is an equilibrium. If B accommodates, I don't want to go here to get 0. And if E enters, she doesn't want to go here instead of and to fight, because then she reduces her payoff from 100 to 50. So this is an equilibrium. But there is another equilibrium. So I can say this is equilibrium and this is the sensible one. But there's another one. Here is another one. Let's check it. Okay? First, you know what? Let's do the stars, so you will see. If I enter, then 150, I designate the 100. If I'm out, 300, 300, both of them. If she accommodates, 100 or 0, 100. If she fights, negative 200 or 0. So I have two Nash equilibrium, this and this. However, I say that this is, the one obtained by backward induction, by folding the tree backwardly. This is another Nash equilibrium, but nonsensible. Why it is nonsensible? Because accommodating for B dominates, weakly dominates fighting. Look here. If she fights, if B fights, she can get 50 or 300. If she accommodates, she can get 100 or 300. So why to fight if by accommodating I'm getting at least as much or maybe more? So as you can see, fighting is weakly dominated strategy. Or accommodating strictly dominates fighting. Therefore, the only sensible strategy for B is to go down, to go accommodate, and therefore E knows it, and then he should say, should I go for 100 or the 0? So clearly, this is the perfect. Again, I refer to perfect the equilibrium that is obtained by backward induction. And this is another equilibrium which is nonsensible. So every time the equilibrium, the backward induction, will be the sensible and the other one the nonsensible. Actually, there is another equilibrium here. Okay. This is also, no, this is not an equilibrium. First of all, I designate. Okay, now I see. 150, I designate 100, 300, 300, and then I designated 100 and 0, I designate 100, negative 200 and 0, I will designate the 0. So there are two Nash equilibrium points. One is with weakly dominated strategy, the other one perfect. So this is the perfect, this is the one that we obtained by backward induction, 100 each. Now, what is this equilibrium with zero? I am out because you fight. I'll tell you what is this equilibrium. Let's write it. Okay, he's out. Why is out? Because B threatened to fight. Out and fight. You get this. Out and fight. So out and fight. So what is this? B is telling E, look, if you are going to enter, if you are not going to stay out, if you are going to enter, I tell you what I do. I fight. And you are going to lose $200,000. E is scared by that threat, and he decides to stay out. But this is non-credible threat, because once E enter, why she should fight? She's going to make 50,000 and not 100,000. So E should not believe the threat of B, because this is a non-credible threat. B is not going to commit suicide. Now, if there is what we call the repeated game, where I will fight to show you that next time if you come on, then you should be careful because you see that I'm ready to fight, then that is not the game here. Then the game may continue and we have to describe a bigger game. This is the case. This game that is described in figure 5 is the case where the entrant make one choice, either to enter or stay out. If he stays out, the entrant disappears, and this game is played only once, not more than that. And everything is, after that, you forget about everything. The entire game is described here. If there is I fight. Why I fight? Because tomorrow there will be another. And let's say tomorrow there's going to be another entrant that would like to enter or not to enter. They will remember that I know to fight. Then you have to describe that another entrant may come in, and then, that's not the game. I agree that maybe in the long run, to establish reputation, that I'm tough and I fight, even I lose, maybe it pays me down the road to do it. But just for this game, we played it once and no entrant anymore. Either I come in or not. Then the only sensible outcome, then it's not a threat, because I cannot threat that I commit suicide. I don't believe you. And therefore, the only sensible equilibrium is this, which we call perfect. So this is the perfect equilibrium. There's another equilibrium, the 0-300, which is nonsensible. Why it's nonsensible? Because to get it, B is fighting. And to fight is dominated by accommodate. Because 300 is like 300, by 50 is less than 100. Why should I fight if by accommodating I can get either the same or more? Therefore, that's the only sensible outcome. Perfect equilibrium. That is, here in these arrows that you see here now, it describes now the other equilibrium where B threatened to fight if he enters, and he is scared. And he said, wow, if I enter, she's threatened to fight, then I'll lose 200. Therefore, I'm afraid I'm going to stay out. Why it's an equilibrium, by the way? Look, if I stay out, she has no, even though 100 is more than 50, she has no incentive to deviate because the game is here and up. And if I enter, so if I stays out, sorry. And then if I decide to stay out, doesn't matter if she fights or accommodate, the outcome is this. And if she fights, surely I don't want to enter to get negative 200, I should stay out. So it's an equilibrium, but that equilibrium relies on non-credible threat, and the strategy of B to fight, in this case, is weakly dominated. There are here two Nash equilibrium points. Enter and for E enters, B accommodates, which is the 100-100, and there is out and fight is the other one, non-credible. This is perfect, okay? This is perfect equilibrium, and this is nonsensible, as I explained. But only one of them, the first point, is obtained by what we call backward induction. The other equilibrium is obtained when B threatens to fight any entry and E, the potential entrant, takes the threat seriously and retreats. Is this equilibrium sensible? We argue that it is not. The threat of B is not credible. If E enters and B fights, then E obtained $50,000. Okay? No, I think B. Then B, we have to change it. If E enters and B fights, look here. If E enters and B fights, she gets 50,000. That was a typo. Then B, in the we are going every time that I do a Zoom lecture, it gives me the opportunity to find typos, and then I'm right after I update also the PowerPoint presentation. So if E enters and B fights, then B obtains 50,000. But if B accommodates E, it obtains 100,000. Thus, E should not believe that the threat of B to fight, and E should enter, because I don't believe that she prefers 50 on 100. Therefore, if she tells me that she is going to fight, I don't believe you. Notice that the strategy fight of B is indeed weakly dominated by its strategy accommodate. The Nash equilibrium, which is obtained by backward induction manner, called perfect equilibrium, PE. And I want to emphasize, it is applied only to dynamic games where player play sequentially. Consider the following game in a tree form. Okay, a simple game. Look here. So player 1 can go left or right. We call it left 1, right 1. If he goes to the right, the game is over. But player 2 does not need to play. He, 1, gets 50. She, 2, gets negative 20. However, if 1 decides to go left, then now 2 has 2 choices. To go left or to go right. If she goes left, okay, then 1 is getting 20 and she gets 7. And if she goes right, then 1 again is called to play, and he can play left 2 or R2. If he goes left 2, he gets 3 and she gets 6. If he goes R2, he gets 4 and she gets 8. That's the game. And the question is, what will be the perfect, the sensible equilibrium of this game? So first we would like to work it backwardly. So good to drink a good soda water. Okay. So let's start from the end. That backward induction, I start from the end. The last one is here. So 1 says, if he's called to play, that means that he played left 1 and she played R. But let's say, I don't care, he got here. What he should do? He says, if I go left, I'm getting 3. If I go R, I'm getting 4. So clearly I prefer 4 on 3. I should go like this. Let me clean it up. 1 will go here at this point. Why? Because he prefers 4 on 3. 2 knows it. And she says, if I go left, I'm going to get 7. Now, who makes the decision here? 2. So I have now to compare the payoffs of 2. And if I go right, he continues here that we already established, and I'm going to get 8. So I have to go down here. And therefore, 1 says, if I go left, I'll end up with 4. If I go down, I'll end up with 5. and this is the only sensible outcome. 5 for me, negative 20 for player 2. Even though they could, they missed the 20 and 7. So I can tell you what maybe, so this is that's the perfect equilibrium outcome. But we'll get into it again, but let me say this. Player 2 can come to player 1 and say, look, I promise you that if you go left 1, I'll continue here. You get 20, I'm getting 7. We're both very happy. Okay? So player 1 may say, well, yeah, that's not bad. I'll get 20. It's good. So he goes in. But then 2, why should continue here to get 7? She knows that if she continues here, 1 is not going to go for 3, it's going to go to 4, and therefore she's going to get 8. So the promise of 2 to go left is a non-credible promise. So let's see how we do it as before, but now again. So here 1 decides either to go left or right to get 3 or 4. He goes for 4. Now next 2 has to make a decision. She knows that if she goes right, 1 will continue right and she's going to get 8. If she goes left, she's going to get 7. So it's clear that she's going to go here. 1 knows it. So 1 knows that if he goes left, whatever 2 will tell him, she will go right. Because she knows that 1 will continue right. So 1 says, I go left, I'm getting 4. I go right, I'm getting 5. So 1 here goes to 5. And this is the equilibrium outcome. Sad as it is, you can't escape it. We can work out the example with transforming this game into a table to figure out all the Nash equilibrium of this game. But this is one Nash equilibrium. By the way, to describe the Nash equilibrium of a game in a tree form, I have to describe what every player does in every of his decision node. What 1 does here, even if it goes down, what 1 does here, what 2 does here, and what 1 does here. That is, by the backward induction, tells me everywhere how should every player play. Okay, so now let's try to, the perfect equilibrium is 5 negative. The perfect equilibrium is, I play here R1, I play here R2, and she is playing R here. That describes the strategy of 1 and of 2 in each one of their decision nodes. Decision nodes where they may take a decision. May. Actually, they don't take. If 1 goes down to right, they don't take, 2 doesn't take a decision and 1 does not take the second decision. However, I have to specify for rational players what they would do if they get to any node where they have to make a decision. So when I talked about equilibrium, I'm talking about the strategy of each one. When I'm talking about the equilibrium outcome, I'm talking about the payoff of each one of them. So this is the equilibrium payoff or outcome. It's the same. Sometimes I'd call it payoff, sometimes equilibrium outcome. And this is the equilibrium strategies. This is equilibrium strategies or simply equilibrium. So when I say equilibrium, I mean equilibrium strategies. Otherwise, I say equilibrium outcome or equilibrium payoffs. Are there other equilibrium points in the game? Yes, there are, but how do I know to figure it out? I move to a table. Let us reduce this game. Let us reduce this game in to a game in strategic form. It is true that 1 has 4 strategies. Here, in what is a strategy? What should I do in each one of my decision nodes as player 1? So here I can go left or right, and also here, left or right. So one strategy is left on both. The other strategy is right on the first one and left on the other one, which is quite crazy, because if I go right, I'm not going to do anything here. The game is over. But still, to be, for the full description, I can reduce the game and just say what happens if I go just right here or left with these two. We'll talk about it in a second. And 2 has 2 strategies, going left or going right. So let's look on it. These are the 4 strategies. But if one, for player 1, if one goes R1, look, if one goes R1, it doesn't matter what 2 does here, because R1 is 5 and negative 20. So you get a generated game. So let's write it slowly. Let's say I'm R1 and left 2. I go R1 and left 2. If you go left or you go right, doesn't matter. This is the game. If I go right 1, namely down, then it doesn't matter what 2 plan to do, because she's not going to call to play. I terminate the game by going R1. If I go, what is this one? What is this one? Again, I'm going R1 here. The only difference between this and this, how I play here. But if I go R1, it doesn't matter how I play here. So actually, this, if you like, formally, this is the game, as you can see. All 4 strategies. Well, what are the 4 strategies? One of them for player 1. One of them R1, left 2. The other one R1 and R2. The other one left 1 and left 1 and left 2. And left 1 and R2. So there are 4 strategies, only 2 for the player, and I can write. This part is trivial. Why? If I go R1, doesn't matter what the other one is doing. Here in both of them I go R1 here, and therefore the game terminates with 5 minus 20, 5 minus 20. So the more relevant one is this part. If I go left 1, then it depends. Let's say I go left 1 and left 2. So if she goes left, 27. If she goes right, 3, 6. Now suppose that I go left 1, but I go here to R2. If she goes left, 27. If she goes right, 4, 8. So that's the description of the game in a table form, what we call strategic form. This is the game in a tree form. This is the game in strategic form. By the way, I could reduce it, and instead of put all this with 5 minus 24 times, to say there are actually 3 strategies of player 1. Whether to go down R1 and that's it, or to go left 1 with left 2 or left 1 with R2. I think that I have it later, we'll see. So first of all, we can find the equilibrium, or let me continue here. Yeah, that's the reduced one. So I can go R1. If I go R1, I don't need to say to do anything. In that case, 5 minus 20, no matter what 2 plan to do here. Otherwise, as I said, L1, L2, and you go left, 27, you go right, 3, 6, and instead, if I go something like this, and you go left at the same 27, if you go right, 4 and 8. So actually, this is the game in strategic form, the reduced game. Why reduced? Actually, I have 4, but 4 strategies for player 1, but these 2 are giving the same thing. So let's find the equilibrium. So if player 1 goes R1, then negative 20, negative 20. If he goes L1, L2, 7 and 6, I designate the 7. 7 and 8, I designate the 8. If she goes left, 20 and 20, I designate both. If she goes right, 5, 3, 4, I designate this. So I have 2 Nash equilibrium. Okay, this, what does mean this? R1 and R. I go R1 and she goes R. Okay, it doesn't matter if I go here or here because the game terminates here. That is the perfect equilibrium. This is the perfect equilibrium. And there is another equilibrium. The other equilibrium is this one. Left 1, left 2, and R. Let's do it. Left 1, left 2, and R. Left 1, left 2, and R. What does it mean? It means the following. Okay? The other equilibrium is this. She, sorry, and left. I was surprised a little bit. And left. Now. I mean, this is the following. Player 1 goes left 1, and she tells, player 1 is approached by player 2 that tells him, you should go left 1. Why? If not, if you don't go to left 1, okay, then, just a second, yes. If you don't go to left 1, I mean, then if you go to R1, you go to 5. I suggest you to go to left 1. Why? Because then I'll go left and you'll get 20. So please do it. This is non-credible threat because once he goes here, player 2 knows that if she goes here, he will continue to go down. Okay? Because he's not going to go for 3, he's going to go for 4. And therefore, she knows that she's going to get 8. And what she promised player 1 is something to go 7. So once player 1 went L1, then the only sensible outcome, if he got... So looking on this subgame, okay, after player 1 makes left 1, clearly, I mean, this... player 1 here, 3 or 4, he will go here, and she goes here to get 8 and not 7. So it's clear how she's going to play in this game. So she tried to convince him to do this, to go left 1, because otherwise if he goes R1, she's getting negative 20. So she says, believe me, but there's no binding agreements. They can talk, but they can do whatever they want. We are in an environment of non-cooperative environment, where they sometimes may talk to each other, but they cannot make a binding contract. So therefore, whatever 2 tells one, he not necessarily should believe her. Okay, once he goes left 1, she's not going to keep the promise to go left. She's going to go right, anticipating 1 to go right as well. So this equilibrium is nonsensical, and by the way, it must be that it uses weakly dominated strategies. And indeed, look on L1, L2 for player 1. He gets either 20 or 3. If he goes down here to L1, R2, he gets either 20 or 4. So this is weakly dominated by this. So it is true that this is an equilibrium, but with a strategy which is weakly dominated by another strategy. Therefore, it is not sensible. So the only sensible equilibrium outcome is 5 for 1 and negative 20 for 2. Okay, so as you can see, this is the situation, and let's continue. Let me just go again. We'll erase all this. Good. And now how we analyze it. So we designate negative 20, negative 20. What is the maximum of the two? It's negative 20. So I designate both. 7 and 6, I'll designate 7. 7 and 8, I'll designate 8. And now what happens if 2 goes left? 5, 20, 20, I'll designate 20, 20. 5, if she goes right. 5, 3, 4, I'll designate 5. Great. So this is, you have 2 equilibrium points. One of them is this is the perfect, and this is the perfect equilibrium, this is the non-sensible. But both of them are equilibrium points. As you can see, this is the equilibrium and it works backwardly. 1 here, compare 4 to 3 goes to 4. 2 here goes, say, if I go R, I get 8. If I go left, I get 7. She goes R. 1, understand it. If I go left 1, I'm going to get 4. If I go R1, I'm going to get 5. And this is the equilibrium payoff or outcome. What are the strategy? Player 1 goes R1 and she goes R. Even though she plans to go R, but she doesn't play the game. Because by going R1, he terminates the game. 2 Nash equilibrium points. The other one, here we describe the other one. It's an equilibrium, but it relies on non-credible promise. Please go left 1 and I'll continue to go here. Okay? You get 20. If you deviate, you get only 5. So, but I don't believe you, Mrs. 2. Why? Because you're not going to go left, because you will see, you're not going to go left, because you know that if you go R, I'm continue. This is based. The reason that I will go like this, okay, it's and by the way, and that's also include a threat of player 1. What is the threat of player 1 here? Look, you promised me to go left. If you don't go left, I'm going, and you go right, let me tell you, I'm going to go here that you'll get 6 and not 7. Okay? But 2 should not believe 1, because why to go here to get 3 and not to go down to get 4? So it based on a promise of 2 that he's not going to keep, knowing that the threat of 1 to convince 2 to go left, okay, can be by threatening to go left 2, in which case she's going to get only 6. She doesn't believe him. She knows that if the game comes here, and that's the end of it. He will take 4 and not 3. So he knows that he's going to get here. Therefore, she's not going, once he goes left, she's not going to keep the promise to go left. She's going to go right to get 8 and not to get 7. A little bit complicated. But you can see it, that this is weakly dominated strategy. Look, 20 is like 20, but 3 is less than 4. So L1, L2 is weakly dominated by L1, R2. As we can see, we have 2 equilibrium points. One is the perfect equilibrium point, this one, the first one. And the other one is where 20 and 7, even though both players prefer the equilibrium number 2, because they get higher payoff, it is not sensible, and will not be chosen. Notice that the strategy L1, L2 of 1 is weakly dominated by L1, R2. L1, L2 is weakly dominated by L1, R2. 20 is like 20, as 3 is less than 4. Oops, sorry. And therefore one will not choose it. Also observe figure 6 that the equilibrium L1, L2, LL is based on a non-credible threat of 1 to play left 2 if 2 plays R. But if 2 indeed plays R, why should 1 play L2? He obtains more if he plays R2. He will get 4 and not 3. The only sensible equilibrium outcome is 5 and -20.